Welcome to bilingual e-lectures for diploma students. Subject electrical drives and control, stepper motor and servo motor and drives. Lecture 12, Unit 3. Permanent magnet DC motor, PMDC. Permanent magnet DC motor is a motor which has got a permanent motor in its stator. If a permanent magnet is used to create magnetic field in a DC motor, the motor is referred to permanent magnet DC motor, or we call this a PMDC motor. This PMDC motor is the same as the DC shunt motor, with the difference that there is a permanent magnet instead of stationary field winding for providing the required magnetic flux. The PMDC motor அப்படினா DC shunt motor மாதிரியே உள்ளது தான். DC shunt motorல வந்து ஒரு வைண்டிங் இருக்கும், shunt field winding, அப்புறம் ஒரு ஆர்மேச்சர் இருக்கும். அதில் அந்த ஷண்ட் ஃபீல்ட் வைண்டிங் எதுக்குன்னா, அதில் ஒரு எக்ஸைட்டேஷன் கொடுத்து நம்ம ஒரு எலக்ட்ரோமேக்னெட் மூலம் ஒரு மேக்னெட்டிக் ஃபீல்ட் கிரியேட் பண்ணுறோம். அப்படி நம்ம செப்பரேட் எக்ஸைட்டேஷன் இங்கே கொடுக்க தேவையில்லை, அதுக்கு பதிலாக ஒரு பர்மனன்ட் மேக்னெட்டே நம்ம இங்கே இன்ஸ்டால் பண்ணிடுறோம். This permanent magnet magnet DC motor is similar to ordinary DC shunt motor, except that its field is provided by permanent magnet instead of salient pole wound field structure. So this is the diagram for permanent magnet DC motor. You have got a rotor. This is the rotor part, which is a rotating one, and then this is a stator magnets. You have got a stator magnets mounted on this. So this is a permanent magnet. So a PMDC motor mainly consists of two parts. One is a stator and rotor or armature. This is the stator part. You have got north pole and south pole, which is a permanent magnet, and the rotor is nothing but your armature. Stator, here the stator, which is a steel cylinder. This stator is a steel cylinder. The magnets are mounted in the inner periphery of this cylinder. The magnets are mounted in the inside, in the inner periphery of the cylinder. The permanent magnets are mounted in such a way that the north pole and south pole of each magnets are alternatively faced towards armature. So this is only a two-pole magnet. The cylindrical steel stator supports the permanent magnet. The stator also provides return path for magnetic flux. The rotor consists of armature winding, commutator and brushes, the same as those in conventional DC motors. The material used for permanent magnet is high residual flux density and high coercivity. For the motors having the ratings up to 150 kilowatt aluminum nickel cobalt alloy, permanent magnets may be used. The ferrite magnets are used in the fractional kilowatt motors, while rare earth magnets, even though costly, are economical in small and large motors. Another form of the stator construction is the one in which permanent magnet material is cast in the form of a continuous ring instead of two pieces. So the previous slide we have seen with the two pieces, instead that they cast into a form of continuous ring. The stator also serves as a return path for the magnetic flux. Rotor, this is a rotor. The rotor of the PMDC is similar to the other DC motor. The rotor or armature of permanent magnet DC motor also consists of a core, windings and commutator. Armature core is made up of number of varnished insulated slotted circular lamination of steel sheets. By fixing these circular steel sheets one by one, a cylindrical shaped slotted armature core is formed. The varnish insulated laminated steel sheets are used to reduce the eddy current loss in armature permanent magnet DC motor. And these slots on the outer periphery of the armature core are used for housing armature conductors. These slots in the outer periphery of the rotor are used for housing the slots. The armature conductors are connected in a suitable manner, which gives rise to armature winding. The end terminals of the winding are connected to the commutator segments placed on the motor shaft. Like other DC motors, carbon or graphite brushes are replaced with a spring pressure on the commutator segments to supply current to the armature. Working of PMDC motor, permanent magnet DC motor, it's like similar to DC shunt motor, and these motors are normally run on 6 volt 12 volt or 24 volt DC supply. So, this DC supply can be obtained from batteries or rectified AC because of the interaction between the flux produced by the permanent magnet and current carried by the armature. A torque is produced and hence the motor rotates. If you see the working of a permanent magnet DC motor, the permanent magnet, it supplies a magnetic field. So, already a magnetic field is existing, we are supplying a current to the armature. So, the conductors are placed. So, because of the current carrying conductor, there is another magnetic flux field is produced. So, the interaction between the permanent magnet and the current carried by the armature, they produce a torque and hence the motor it begins to rotate. If you see the materials used in the PMDC, permanent magnet used for is a high residual flux density and coercivity. Up to 150 kilowatt alnico is used, and then ferrite magnets are used in fractional kilowatt motors, while rare earth magnets are costly and they are economical in small and large motors. So, this is this diagram shows a permanent magnet. There are 3 types of permanent magnets used for such motors. Alnico is aluminum nickel cobalt magnets. They are used up to 1 kilowatt to 150 kilowatt. Ferrite magnets, they are much economical in fractional kilowatt motors, fractional half horsepower motors, say half HP, quarter HP. So, ferrite magnets are used in smaller one. And rare earth magnets, it is made up of samarium cobalt and neodymium iron cobalt, which have the highest energy product. Such magnetic materials are costly but are best economic choice for small as well as large motors. Advantages: no need of field excitation arrangement. So, when you see the other DC type of motors, previously we require a separate excitation, whether it is a self excited machine or separately excited, we have to provide a excitation to the field to produce a magnetic field. So, here no need of field excitation arrangement, this is one of the major advantage. No input power is consumed for excitation, which improves efficiency of this DC motor. No field coil, hence space for field coil is saved, which reduces the overall size of the motor, and this is cheaper and economical for fractional kilowatt rated applications. Low voltage PMDC motors produce less air noise. Since their magnetic field is active at all times, even when motor is not being used, because of that their temperature tends to be higher. Applications of PMDC motor. PMDC motor is extensively used where small DC motors are required and also very effective control is not required, such as in automobiles, automobile starters, toys, wipers, washers, hot blowers, air conditioners, computer disk drives, food mixers, ice crusher, drills, saws, portable vacuum cleaner and shoe polisher. So, this is very widely used in all of the Chinese toys. So, this is very much widely used, this permanent magnets by the Chinese people. Next one is stepper motor. Stepper motor does not run continuously, but rotates in jerks or step in either direction when a electric pulse is given to it. Thus, it is a very useful digital device. So, stepper motor is a one which goes on step by step arrangement. It will, if you give one pulse, it will move for a particular degree. If you give another pulse, it will move for the same particular degree. So, it moves on jerks, step by step. So, that is why its name is called as stepper motor. So, it is a very much useful in the digital service. Stepper motor, the stator consists of 3 or 4 phase windings which are kept in uniformly distributed slots. So, you can see the diagram. So, this is a stepper motor, this is a rotor and this is stator. So, stator consists of 3 or 4 phase windings which are kept in uniformly distributed slots. It has a rotor of unexcited salient poles or salient poles with permanent magnet excitation. So, the number of stator and rotor poles depend upon the required angular shift per pulse. So, how many degrees you want to move the stepper motor in each step, for step, depending upon that only your stator and rotor poles are designed. So, this stator consists 3 or 4 phase windings which are kept in uniformly distributed slots. It has a rotor of unexcited salient poles or salient pole with permanent magnet excitation. Stepper motor is an electromagnetic energy conversion device that converts electrical pulse to discrete mechanical movements. These motors are also called stepper motor as stepping motor or stepper. Due to its nature of its working, it is primarily used for position control systems. If you want to place exactly in a particular position to find out that position, this type of stepper motors are used. A step in stepper motor is defined as the angular rotation produced by the shaft of the motor each time it receives a pulse. Each step causes the shaft to rotate a definite number of degrees. So, the 360 degrees we divide into so many step angles. The angle through which the motor shaft rotates for each command is called the step angle beta. Step angle equal 360 degree by number of stator phases multiplied by number of rotor teeth. Based on the construction of the magnetic circuit, there are 3 main types of motors. One is a permanent magnet stepper motor which has got a high torque, low angular resolution. Then variable reluctance stepper motor, excellent angular resolution, low torque. And then hybrid stepper motor which combines the both is above permanent and variable reluctance, provides good torque and angular resolution. Coming to the construction of permanent magnet stepper motor, it has wound rotor stator poles. So, these are the stator poles which are all permanent magnets, wound rotor stator poles and permanently magnetized rotor which is constructed in cylindrical shape. Its direction of rotation depends on the polarity of stator current. Whether if it is rotating in clockwise or anti-clockwise, the polarity depends upon the stator current. The rotor is on the inside is the rotor with permanent mags mounted on its perimeter. The stator is on the outside with electromagnets called windings. So, the controller energizes the windings with pulses of DC current. So, many of these windings are connected together. Each group of connected windings forms a phase, usually of 3 phase or 4 phase. The stator has 12 windings and its rotor has 6 magnets mounted on its perimeter. Permanent magnet steppers are generally 2 phase motors. In the figure, the different phases are denoted as A and B. A, B, A dash, B dash. So, A, B, like this they are denoted A dash, B dash, A, B. The windings labeled A dash and B dash receive the same current as those labeled A and B, but in the opposite direction. That is, if A behaves as a north pole, then A dash behaves as a south pole. Each winding has one of 3 states: positive current, negative current and 0 current. Here positive current implies a north pole and negative current implies a south pole. It illustrates a single turn 30-degree rotation of a permanent magnet stepper motor. In the windings, a small n implies that the winding behaves like a north pole due to the positive current. A small s implies that the winding behaves like a south pole due to negative current. The rotor rotates so that its poles align with the B and B dash windings. The rotation angle equals the angle between the A and B windings, which means the rotor turns exactly 30-degree in the clockwise direction. Variable reluctance stepper motor. In a variable reluctance stepper motor, the rotor turns at a specific angle to minimize the reluctance between opposite windings in the stator. It has the wound stator same as that of the permanent magnet type, but the rotor is a non-magnetic one, this variable reluctance one. The rotor is made up of ferromagnetic material. When the stator pole is magnetized, the rotor teeth will align with the magnetized stator pole. It is called variable reluctance motor because the reluctance of the magnetic circuit formed by the rotor and the stator teeth varies with the angular position of the rotor. There are two primary differences between variable reluctance stepper motors and permanent magnet steppers. Rotor, unlike the permanent magnet stepper, the rotor in a variable reluctance stepper does not have magnets. Instead, the rotor is an iron disc with small protrusions called teeth. So, this is all small protrusions called teeth. Phases, in a permanent magnet stepper, the controller energizes windings in two phases. For a variable reluctance stepper, the controller energizes every pair of opposite windings independently. In other words, if the stator has n windings, it receives n by 2 signals from the controller. And this figure illustrates the rotor and stator of a variable reluctance stepper. In this motor, the stator has 8 windings and the rotor has 6 teeth. 8 windings and 6 teeth. The A and A dash windings are labeled and N and S, which shows how they are re-energized by the controller. The teeth in the rotor align with these windings to provide a path for magnetic flux between A and A dash. And the controller has delivered current to the B and B dash windings and the rotor has aligned itself accordingly. In the figure B, the C and C dash windings are energized, which moves the rotor 15 degree in the clockwise directions. If we know the number of windings in the stator and the number of teeth on the rotor, the step angle of a variable reluctance stepper motor can be computed with the following equations: 360 degree into Nw minus Nt divided by Nw into Nt. So, this figure shows Nw equals 8 and N teeth equals 6. Therefore, the step angle can be computed as 360 degree into 2 by 48, which is equal to 15 degree. So, the angle resolution given by the improved by increasing the number of windings and teeth. So, each step is determined by the number of phases and teeth. So, again this is a hybrid stepper motor which combines the features of both permanent magnet type as well as variable reluctance type. Applications of stepper motors. These motors are used for operation control in computer peripherals, textile industry, IC fabricators and robotics. So, applications requiring incremental motion are typewriters, line printers, tape drives, floppy disk drives and XY plotters. This is especially used in robotics control for each of its steps. Whether it is every movement, stepper motor is a very important in robotics motion control, because it gives a exact position control. And next one is a servo motor. The motor that are used in automatic control systems are called as servo motors. When the objective of the system is to control the position of an object, then the system is called servo mechanism. Previously we have seen about stepper motor, again which is giving a position control. The servo motor is also one of the best motor which gives a very good position control. The servo motors are used to convert an electrical signal applied to them into an angular displacement of the shaft. They can either operate in a continuous duty or a step by duty depending on the construction. So, this is a brushless servo motor. So, the structure of the brushless servo motor is shown in this diagram. You got a stator and got a armature winding, and this center one is a rotor which is a permanent magnet. So, this is a rotor one, this is a stator which is a permanent magnet. The stator consists of an armature core and armature winding. The armature core is made up of laminated punched silicon steel sheet of 0.35 to 0.5 mm thickness. The armature windings are similar to AC motor and are usually distributed in a 3-phase type. Stator, the windings are designed according to the drive specification, which require either a sinusoidal or a trapezoidal back EMF waveform. So, this stator windings are designed according to the waveforms, whether you want a sine wave or a trapezoidal wave. The factors governing the design are number of stator slots, pole shape, winding coil pitch, and then number of rotor poles and magnetic shape. This is the rotor. The rotor carries the permanent magnet and is fixed on the motor shaft. The shape of the magnet is either cylindrical or salient pole. Cylindrical is a one which do not have any projection. Salient pole is a one which has got a projection. So, this is a actually it's got a projection, salient pole. Rare earth magnet has also used to improve the performance of the motor. They can be operated up to the boundary of high speed rotation without decreasing the maximum torque. So, this can have, if it is a cylindrical type, which will give you a very good speed rotation. The heat dissipated in the shaft diffuses in the air through the frame because it has got gap in between them. Salient pole is a projected one which has got gap in between these things. So, the air heat dissipation is very good because of the free flow of air. It is therefore easy to cool the brushless servo motor. Applications of brushless servo motors. These servo motors are best suited for low power applications, and these motors are widely used in aircraft control systems, electromechanical actuators, process controllers, robotics, machine tools used in instrument servos, computers. So, this permanent magnet servo motor field control is not possible in the case of permanent magnet DC motor, as the field is permanently magnet. So, DC servo motors working principle in that case is similar to that of armature controlled motor. So, in this type of motors, the field winding is replaced by a permanent magnet to produce the required permanent magnetic field. Permanent magnet motors are economical for power ratings up to a few kilowatt. So, first we have seen about brushless servo motor. This is a permanent magnet servo motor. So, it has got a permanent magnet in the stator and the rotor is here. The construction of permanent magnet servo motor. If the permanent magnet servo motors armature is placed in the rotor and the permanent magnet poles are fixed in the stator. So, these are the poles fixed in the periphery here, the rotor is in the armature windings are placed. The rotor employs special types of construction to reduce the weight and so the inertia of the rotating system. So, special type of construction is cylindrical armature with a small diameter and longer axial length, disc armature and hollow armature. Advantages: a simpler, more reliable motor because the field power supply is not required, higher efficiency, and field flux is less affected by temperature rise, less heating and no possibility of overspeeding, a more linear torque versus speed curve. If we see the disadvantage, the magnets deteriorate with the time. The magnets demagnetized by the large current transients. So, the permanent magnet servo motors are commonly used in printers and disk drives and tape drives, again used in industrial robots, used in numerical controlled milling machines, CNC machines and milling machines, they are using this. So, in this episode if we see, we have seen about what are the permanent magnet types of motors, PMDC motors and servo motors. The permanent magnet DC motors is one which is widely used in industrial robots. And then the servo motors is again it has got a brushless servo motor and permanent magnet servo motors. So, these motors are widely used in industries, especially with numerically controlled machines, which we called as a CNC machines, milling machines and industrial robots. These motors are especially used for position control and exact position control. So, this is in automatic processing system, these motors are widely used. Similarly, in toy industries like brush, whatever the about industrial drives we will see in the next episode. Thank you.